This is Jack Jackson. In this video we're going to be talking about the divergence theorem. The divergence theorem is one of a few vector versions of something similar to the fundamental theorem of calculus from Calculus 1. So let's start by getting the comparison by thinking about what the fundamental theorem of calculus says. The fundamental theorem of calculus says if we're integrating a derivative, then we can find a definite integral by evaluating the antiderivative of the given derivative function at both boundary points and subtract. So the definite integral from a to b of f prime of x dx is just the f of x evaluated from a to b, that is f of b minus f of a. The divergence theorem says if we're integrating a triple integral, the divergence of a vector field, divergence is a type of derivative, over a volume, then we may find the value of this triple integral by integrating along the boundary of the 3D region, which is a surface. So that would be a flux integral or a surface integral. Okay, and with this theorem we may turn a triple integral into a surface integral, and more importantly the other direction, we may turn a surface integral into a triple integral. So the way this goes, if we let W be a solid 3D region and let S be a surface, which is the boundary of W, and S is piecewise smooth and oriented outward, then the surface integral or flux integral of f dot dA is the triple integral of the divergence of f dV. We do need to have the field defined everywhere on the inside of that volume as well as on its surface. Let me add that. All right. So let's put this into work a couple of places. Let's do a couple of examples. So let's find the flux out of a sphere of radius 10 centered at the origin for the following vector field. F of xyz is x squared, comma, y minus 2xy, comma, 10z. So notice that if we're going to do this, we're talking about a flux integral or a surface integral. If we do this directly, we're going to have to parameterize this sphere, set it up as a flux integral and work it out. Okay, but because this sphere is a closed surface, it's oriented outward, and the vector field is defined everywhere on the inside of the sphere as well as on the surface of the sphere, we can apply the divergence theorem, which is going to make this much easier to do. Okay, so to do this, we need to find the divergence of this field. Okay, and of course that's pretty easy to do. You just do the partial derivative with respect to x, the first one, plus partial derivative with respect to y, the second part, plus the partial derivative with respect to z of the third part, and add them together for that. So the derivative of the first part with respect to x is 2x, the derivative of the second component with respect to y is 1 minus 2x, and the derivative of the third component is just 10. The 2x's cancel, 1 plus 10 is 11, so the fact that divergence is just a constant. And that makes this one really easy to do, because now the surface integral of f dot dA of this function over that surface is the triple integral over that sphere, not just the sphere, but the inside of the sphere as well, of the divergence dV. But the divergence is 11. We'll pull that 11 out front, we've got this triple integral. That triple integral is the volume of that region. Okay, but that region is just a sphere. We know the formula for the volume of a sphere. It's just 4/3 power cubed. So we can do this one without actually having to find any antiderivatives there. Just plug that in, work out the arithmetic there. That's 44,000 pi over 3, or about 46,077 for what we set out to do, which was find the flux out of the sphere. How about another example? Find the flux of the following vector field F, which is given by x squared, comma, y minus 2xy, comma, 10z, out of this box, rectangular box, where x goes from 1 to 3, y goes from 2 to 5, and z goes from 0 to 4, just a good old right rectangular prism. Now, if you think about this, to do this directly, we have to set this up as a flux integral. We'd have to parameterize this surface. Well, this surface is not just one smooth surface. It's actually 6 pieces, 6 parts of 6 planes. So to work this out directly, we would have to parameterize all 6 of those, break it down into 6 different integrals, find the flux out of each of those sides, and then add them up. Okay, we could do that, but it would be too hard because they're just planes, and they're just constant planes at that. But nevertheless, it's going to be easier if we can do this with the divergence theorem. This is a closed surface. It's oriented outward. This function is defined everywhere on the inside of that box as well as on the edges of it. And so we need to find the divergence of this vector field. So we take the partial derivative with respect to x in the first part. That's just y. Partial derivative of y with respect to y in the second part. That's going to be minus 2x z squared. And where did I don't know where that 1 comes from. I think that's extraneous here. Hang on a minute. And the third part is the partial derivative with respect to z. That part's 0, and that part is 3z squared. So the divergence is the scalar function y minus 2xz squared plus 3z squared. And we want to then work that out as a triple integral. So we can see this flux integral or surface integral can be set up as a triple integral of the divergence times the dv. Now, since this is really nicely set up as a rectangular box, it makes sense to use rectangular coordinates. So dv can be dx, dy, dz. Actually, any order, it doesn't really matter too much here. But if we put dx first, that x is run from 1 to 3. Then dy, y runs from 2 to 5. And we integrate with respect to z last, z runs from 0 to 4. So there are no variables in this because of the shape of the region. And the divergence is just this polynomial function here, so it's not going to be too hard, even though, I mean, it is a triple integral, so we're going to have a few lines to work this out. But very straightforward. Take the derivative with respect to x. Let's see, this is going to pick up an x, so xy. That x is going to go up a power and divide by 2, so this is going to be minus x squared z squared, and that's going to have an x in it. Evaluate from 1 to 3, we place 3 in place of all the x's, and 1 in place of all the x's, and simplify. So that's 3y minus 9z squared plus 9z squared minus y plus z squared. Oops, let's see here. Plus z squared. Let me fix that. And then minus 3z squared. Okay, so let's see, where were we? So there was that. We plug that in and simplify. 3y minus 9z squared plus 9z squared minus y plus z squared minus 3z squared. Okay, combine like terms. You get 3y minus 1y is 2y. These two terms cancel out. 1z squared minus 3z squared is minus 2z squared. Evaluate that from, well, we're going to do another derivative, new antiderivative now, with respect to y. So that goes up to y squared. Divided by 2 cancels the coefficient. This picks up a y minus 2yz squared. Evaluate from 2 to 5. So plug in a 5 there and there. Minus plug in a 2 there and there. Okay, that looks good so far. That's 25 minus 10z squared minus 4 plus 4z. Okay, and combining like terms, 25 minus 4 is 21. Negative 10z squared plus 4z squared is negative 6z squared. Take the derivative, antiderivative with respect to z, you get 21z. This goes up to the third power. Negative 6 divided by 3 is negative 2. Evaluate from 0 to 4. Plug in 4's and zeros. These last two are 0. 4 times 21 is 84. 4 cubed is 64 times negative 2 is negative 128. Plus the 84 is negative 44. So that's a lot easier to set up and do as a triple integral than it is as to have to parameterize everything and break it into 6 integrals. and do it as a surface integral. So you can see the usefulness of the divergence theorem when it applies.